I'm Anne-Marie Justin. I'm a senior research engineer with Hewlett-Packard Enterprises, and with me is Srikanth Vardhan. We will be co-presenting this. So this presentation is about unified knowledge platforms. We look into the agentic and generative AI workloads, its challenges, and how storage can effectively address them. So storage has evolved from being passive systems with just reads and writes to insight engines for AI agents. During this period, we have also seen AI evolving, and the evolution in AI has influenced features in storage. In 2000, it was the era of big data, and we saw features like metadata tagging and analytics built into storage. The decade of 2010 was the decade of deep learning and machine learning, and the advancements made in that domain got incorporated into storage and to make the storage more performant, scalable, and more optimized. At present, we are in the agentic AI era, and we see new features getting introduced into storage, such as semantic search, natural language interfaces, and real-time insights for AI agents. Now, what caused this transformation? We have seen the advancements in generative AI. We have seen how the hardware and compute has improved its capabilities over the period of years, and the software stack. So in 2017, ever since the paper Attention is All You Need has came out, there has been rapid developments in the NLP domain, and we saw foundational models like GPT. So GPT 3.5, in 2023, it had an evaluation score in GPQA benchmark somewhere around 30. So GPQA is a benchmark which is used to evaluate this foundational model. It's a graduate level question answering data set which is used to evaluate models. And in 2023, it had an evaluation score somewhere around 30. Whereas right now, the current leaderboard model has an evaluation score around 88. So there was rapid improvements in these capabilities of these foundational models, and this enabled it to be able to use them in the enterprise AI workflows. And we've also seen how the GPUs have improved in its capabilities. Like the current generation of NVIDIA Blackwell GPUs, they have at least 3x more performance than the earlier generation of the Hopper GPUs. So combined these two factors, the algorithms have improved multiple times. And along with this, the software stack, we have frameworks like Llama Index, LangChain, which lowered the barrier for adoption of these generative AI workflows into storage. Along with them, there was open source models that are released into repositories like Hugging Face. Then there are inference engines like Ollama and BEI, which enabled these enterprises to use on-prem inferencing rather than having to rely on a cloud to do inferencing on the cloud. This evolving ecosystem allowed them to do inferencing on-prem. So all these factors led to adoption of these generative AI and agentic workflows in enterprises. Now, to get a perspective, if we look back, some of the features that were introduced into storage, which was driven by the AI innovations, we see features around the fundamental capabilities of the system. There were improvements in the compression algorithms, the better policies for caching and tiering. Then there were also innovations around reducing cost and improving the customer experience. Like features like capacity prediction helps to customer to anticipate the future requirements and be able to plan accordingly. Features like proactive diagnostics helps to understand the bottlenecks in the system. In addition to these features, there was also features driven into storage by the requirements of the AI and ML workloads, especially the training workloads. So for the training, it needs a high throughput write for these checkpoints and low latency read to have the optimized training. And we see features like GPU direct, disaggregated storage, all coming out in response to these requirements. So in summary, these AI-driven innovations previously was mostly storage-centric, or driven by the requirements of the training phase of the AI/ML workload. Now, if we move to the agentic storage systems, the focus shift from the training stage of the workload to the inference stage of the workload. So with the trained models, these trained foundational models, we are now able to infer on data to able to derive insights from it. So the focus, in addition to being storage-centric, this is also data-centric. So at the heart of this system is an AI agent which can independently plan, reason, and execute. And with the right set of tools exposed by the storage, it is able to do actions on the storage. So the user can interact with the storage using natural language queries. And the AI agent knows how the data is stored, how it is organized, how to derive insights from it, how to fetch it. So the user using natural language can do actions like storage administration, read and write of data, search data and metadata. Also, it can be part of this agentic AI workflows where the agent can take an action based on an event that happens, and it could be a transformation in data or enriching the data. So in summary, these capabilities enables automated, intelligent orchestration of workflows. It reduces the complexity for the end users, and it elevates the storage to knowledge platforms. Now, if we dig a little bit deeper on some of these AI, features which can unlock value of data. So we have features like retrieval augmented generation, in which knowledge in LLM is augmented using external knowledge. Like in this case, it's the knowledge that is there in the repository. So with that, the LLM provides context-specific responses. So this enables the users to chat with their data. Features like natural language interfaces enable user to interrogate the system. Like what are it can query the system metadata and custom metadata. So it enables queries like, give me all the documents that got uploaded on a specific date. Or it features like semantic search, where the search is not limited just to the keyword search, but the search is on the semantics of the word or the meaning of the word. So the search is not limited by a regular expression match, but instead it incorporates the meaning in the words. So the agenting infrastructure management enables management of infrastructure through agents. Example, you can do actions like create bucket, create policies, etc. For the storage to take part in these agentic workflows, it needs to expose its data, metadata, and system metadata in a secure manner, and that can be done through standardized protocols like model context protocol, which is used to expose capabilities of the system to the agent. Or it could be through the software development kit, which enables the other agentic workflows to incorporate the features in the storage in its workflow. Now, so far so good, but what are the challenges? So it's not trivial to accomplish all this at an enterprise scale with the security and the performance that is required. A recent study from Gartner said that 87% of the RAG workflows or the RAG infrastructure fails, not because of the inadequate models or the poor quality of data. It's because of the infrastructure choices that have been baked into the system. So these workflows are not the typical application workflows. These have a different set of requirements, and the infrastructure should be designed to be able to satisfy the unique requirements of these workflows. In the next set of slides, we'd see what are the unique requirements of these workflows and how storage can satisfy that. So data is the fuel for the agent, and it needs data, not just any data. It needs governed, structured, contextualized, and accessible data. So for features like RAG and semantic search, you need the data to be transformed to embeddings. So embeddings are high-dimensional numerical representations of data. So it embeds the semantic meaning in the data, meaning if there are two objects which are semantically closer or two objects which are very similar, then their vector representations will also be close together in the vector space, meaning the distance between these vectors will be smaller. Whereas if you have two objects which are very dissimilar, then they will be far in their vector spaces, and the distance between these two vectors will be larger. So in order to enable features, like RAG, where the query is based on semantic similarity, you need to convert the raw data to the form of embeddings. For agents to be able to get insights from the data, to be able to contextualize the data, it needs to extract insights from it. For example, it could be like in an image, identify what is there in the image and add that as metadata or custom tags inside it. Certain workflows requires you to convert the structured data to convert the unstructured data to structured data. For example, in medical domain, like a doctor's notes should be converted into a structured template. So these last two workflows, like the custom metadata or the structured data, these data representations and these workflows are very familiar workflows for storage. But the vector representations and that workflow is something which is relatively new in storage, and the next set of slides will look into that. So in case of RAG, for a query, the incoming query is converted to its vector embeddings, and a similarity search is done on the incoming query with all the vectors that are there in the vector DB. Unlike traditional SQL-based queries, traditional SQL-based queries are based on well-defined SQL indexes, which touch maybe thousands of records, and it's basically sequential access that you do over there. But vector search are usually done on graph indexes, and each of these search involve nodes which are in the diverse regions of this graph network. It's an approximate search over the entire graph. So each query could touch many nodes which are far apart in this graph network, and that leads to a random access. So you need high-performance random read to be able to satisfy these queries at the low latencies. The second aspect is how you do the similarity search. So when you do the similarity search, you need to do the similarity computation of the incoming embedding with what is already there in the vector DB. So that involves high-dimensional mathematical computation, and the underlying system should be able to do these computation in parallel scale. So it needs massive parallel computation capability from the underlying infrastructure. Now, if we go into a little details of these embedding models, so this graph actually shows the embedding model's performance. This is from the MTB leaderboard, which is a benchmark for evaluating the performance of the embedding models. And this benchmark evaluates its performance on an average of multiple different tasks, tasks could be like semantic retrieval, clustering. So these different tasks are used to evaluate these models, and the y-axis shows the average across these tasks. But what I want to focus with this graph is the key characteristics of this embedding model. So these embedding models are defined by their number of parameters in the model. So the number of parameters defines what is the resource required for these embedding models, how much memory you need to load these models and to perform computation and to do the vector embeddings with it. The number of parameters and the max token, which is what is the input text length of this incoming text. So that defines what is the working set memory for your each request that you get. So as the number of parameters increases, the memory required to load these embedding models also increases. And as the max token increases, you need more memory as your working set memory. Also, the size of each of these nodes is the size of the dimension, or which is the size of the output output dimension of the vector. So as the number of dimensions increases, the discriminative capacity in these vectors increases, it will be able to distinguish between two vectors. So that also puts a upper limit on what is the size of your data corpus. So as the number of dimensions increases, your discriminating capacity increases, but that also means the storage that is required to store these vector embeddings increases. So in case of RAG, input text is chunked into different chunks, and each chunk could be around 500 tokens. Each token is 2 to 3 characters. So if you have a 10 KB text of 5, then you could have 5 chunks of each of 500 tokens. And vector embeddings are calculated for each of these chunks. So, and if you have a high dimension of 4096, and if you do the math, this 10 KB will get translated to around 120 KB if you are storing this at 32-bit precision. So there is a significant bloat in the storage that is required to store these embeddings. So, and the exact storage size would depends on the number of dimensions that you have on these vectors, and also the precision at which you are storing. So your system needs to factor in this part. Now, these models are also compute intensive. Like if you take a one H100 GPU, and if you have a request where each request is around 500 token, so you get around the throughput of 30K to 120K requests per second for an 8 billion model. So if you do a back calculation, this somewhere around few MB per seconds. But the storage throughput is on GB per second. So if you have high velocity storage workload, then this embedding calculation will introduce a significant back pressure on your workflow, and you need to accommodate for that. The exact number of throughput, the exact request that you would get depends upon the hardware and the software stack. It depends upon whether you're using a quantized model or not, and what hardware, whether it will depend on the capabilities of your GPU and CPU. But there will be a significant lag for your embedding computation compared to the storage throughput. Now, if we look into the network consideration for this AgenticAI workload, this RAG pipeline involves multiple different modules, and there is a significant amount of data transfer that happens from one module to another. So when the documents are ingested, you need to extract the text out of the document and provide it to the inference endpoint to calculate the embeddings. And once the embeddings are calculated, you store that again to the vector DB. So data transfer happens at each of these points. And the documents chunked are stored in a document store. So when a query comes, again, query has to be converted to embeddings, and on the converted embeddings, a similarity search is done, and based on the top case, similar vectors are retrieved, and their corresponding text is given to the LLM to do the inferencing on. So as you can see, it involves significant amount of data transfer from point to point, and these operations are also latency sensitive. Like the user is now waiting for your answer to come back, and he needs to have it in a couple of seconds to get that better user experience. So your network should have high bandwidth, it should be capable of doing high bandwidth transfer, should have very low read latencies also. And there is a significant east-west traffic that happens in these networks. So in addition to this high volume of data transfer and the latency sensitivity associated with these operations, there also is a problem of query amplification. So usually in a single RAG query can result in multiple different LLM calls. Like if you have a re-ranker, then you need to rank the documents that are retrieved and see which are the top matching documents, and that is given to the LLM. So the re-ranker is also another LLM. So there is a query amplification that happens. And if you are iteratively refining your answer, that also incurs multiple different LLM calls. And especially in agentic workflows where the reasoning is involved, one task should be decomposed to multiple different tasks, and all of this involves multiple calls to the LLM. So significant amount of query amplification, which leads to higher network bandwidth utilization, happens in these workloads. If we look into the memory considerations, the three main components which hog maximum amount of the memory is the LLM and the embedding model and the indexes and the vector indexes. So approximately for every billion parameters, you need around 2 GB of memory to load these models. The exact amount depends upon the precision of these models, whether it's a quantized and also the context length. And in case of indexes, it depends on what is the type of index you have on the vector DB, whether you have an in-memory index like HNSW or if it's a disk index like disk-ANN. So these indexes, you need to factor in the memory requirement of the indexes, the memory requirement of the LLM, and the memory requirement of the embedding model. So these were some of the infrastructure challenges that we have seen from this. And now we'll see the challenges related to the data. So if you look at the data usually is multimodal. You have text, you have PDF, images, audio, and video. And each of these modality would require a specialized treatment. So there is no one-size-fits-all. So the parsing could be different, the chunking strategy would be different, and all of that has to be factored in. And many times these are real-time data streams that come in. So it could be log streams, it could be medical images, and the customer expects that as soon as the document is there, it's ready to be queried, and your system should be capable of absorbing that. So when there is an update in the document, the vector embeddings associated with it should be updated. If there is a delete in the document, that the vector embeddings associated with it, it should be deleted, so that there is no inadvertent leak of information, there is no data leakage, when you do the RAG query, you are not getting responses from a deleted object. And the most important factor in the enterprise data is the data governance. So now the data has been, there is the primary data, the enriched data and metadata, and the vectors, and all of them should be governed by a common set of policies and with a common authentication and authorization mechanism. So if you have 3 different systems, there are 3 failure points for your security, and the chances of having leakage of information or wrong data being exposed to the users would be high. And most importantly, there should be security. Data must be also protected from the undesirable actions from the agent. So with this, I pass it to Srikant to take us to how these challenges have been solved in X10K.
Can you hear me? Yep. Thanks, Anne. So, considering the limitations of current generation systems that Anne talked about, it's clear that we need a fundamental shift in how we think about storage architectures. And we believe that the right approach is one where the data intelligence is pushed down into the storage layers. And this unlocks several benefits, which are shown here. Firstly, it lowers the latency and the time to inference, because all of the processing for extracting the vector embeddings happens as the data is coming into the storage. It reduces the network traffic because, as Anne showed, there's a lot of unnecessary movement of data if there is an external client that's reading the data to extract the metadata. Instead, all of this happens within the storage itself. And a well thought out storage architecture also eliminates unnecessary east-west movement of data within the storage. It also brings streamlined data management by eliminating the complexity for implementing data pipelines outside of the storage. It all happens automatically. And then finally, standardizing the data services, because there's now a single source of truth for the data within the storage, as opposed to maintaining multiple copies of the data and then keeping them in sync. which also exposes potential for losing accuracy in the search results. So at HP, we've been working on this new platform for unstructured data called the Alletra MPX 10K. It was released less than a year ago. This is a scale-out software-defined platform. It currently supports the S3 object protocol natively. It's scalable with a fault-tolerant design, no single point of failures, and it delivers extreme performance and efficiency for AI workloads. It's built to leverage the performance of flash media. It has a optimized log structured key value store as a storage engine. It does efficient erasure coding for data protection and has data reduction inline. And to address some of the compute needs that Anne talked about, it's based on a disaggregated or shared everything architecture where, depending on the compute or capacity needs, you can scale independently for each of those vectors. So if there's a need to add more processing to do all these expensive calculations for embeddings, you can just add compute nodes, and as your capacity scales, similarly, you can just add more compute. So it's clear that we're moving into a stage where storage performance is essential not only for training but also for inference to do all of the processing for RAG at scale. So traditionally, object protocols like S3 were built for sort of cheap and deep and archival use cases, but there is now a shift towards high performance workloads, including AI on top of object stores. And S3 being a protocol that runs on HTTP and TCP, as most of you know, there's a lot of inefficiency in the I/O stack because of the various memory buffers and data movement in the I/O stack. So similar to RDMA for file protocols like NFS, we've been working on RDMA for S3 in collaboration with NVIDIA. And this uses HTTP for all the control messages, but does the data transfer over RDMA, right? So this is a feature that's been recently released. It's the performance numbers are out in public, but gives obviously like massive gains in throughput, latency, and reduces the CPU utilization. So this is really a key piece of the architecture for enriching the metadata inline in the data path. Okay, so here's how the X10K brings all this data intelligence into the storage layer. So as the data is streaming in from various sources, the X10K will automatically recognize the type of data, and it will trigger the appropriate pipeline. So if it's a text, a document, or PDF, it will trigger the extraction of the text, the chunking, and the embedding calculations, and it will then represent that metadata with references into the data itself. So that avoids duplication of the data and having to store copies of it. And as the data itself ages over time, the metadata is automatically kept in sync with the data. So for consumers of this data, it could be AI applications or agents, they are always seeing the latest, most current version of the data. So all of this is handled within the storage in the X10K. So we've also introducing an SDK to simplify the usage of this, and we've debated for a while as to the use of an SDK, but we believe it's the right approach because it brings several advantages. It allows the storage to be decoupled from the application layer in terms of the representation and persistence of the metadata, because application is interacting through the SDK. It allows automatic management of the metadata lifecycle, as I described, because as data is undergoing changes through the SDK, we're able to keep the metadata in sync with the data. On security and the data governance aspect, all the access is through the SDK, so it's a unified set of users and permissions for the data as well as metadata. Customers don't have to create a separate set of users or permissions for RAG. It's all unified, and it's fitting with the existing ecosystem. The SDK is built on top of well-known frameworks like LangChain and Llama Index, and to support agentic access. It's integrated with model context protocol. So this is an open source SDK. It's available at that link mentioned here. I would encourage folks to look into that link for more details. So with that, we'll do a quick demo. It's a two-part demo. So the first one, and actually this is a real-world demo based on the actual usage of this feature within the legal organization in the company. So this is actually a real use case. So the first part of this demo will show creating a document and then making transformations on that document, and then from an end user perspective, doing RAG queries, always seeing the latest results from the search. Okay, so this is a recording, so let me kick this off. So this is the UI, and so the first thing we're going to do is upload a new document. This is a legal document with some policy information. And then once this is uploaded, automatically the XTendK recognizes it's a PDF. It triggers the extraction and references the metadata into the actual data itself. So then we're going to switch to the UI for the query. We log in as a user named user1, and we issue a simple query saying what are the incidents to be reported by supplier. So this immediately recognizes a reference to the document we just uploaded, uses that as a context, and produces the results. So the next thing is we're going to upload a new version of that same PDF with some updated policy, and this will automatically trigger the extraction. It will obsolete the previous metadata, and now the search results for the same query, you will see now returns the most up-to-date results. And finally, we're going to go ahead and delete this document and run the same query, and now it'll just say that it doesn't have the context to respond. So all of this is handled by the storage itself. Okay, so that's the first part of the demo. Now jumping to the second part, this is about the data governance and access control. So in this example, we have two buckets, one called legal general information, the other one is legal sensitive information. We have some users with access to one of these buckets and other users that have access to both these buckets. So to start with, we have user 1 that can only access the legal general bucket. Then we have user 2 that can access only the legal sensitive bucket. So we log in as user 1 who cannot access the sensitive bucket and ask a question about bonus, and the response, because it's going through the same authentication authorization rules. It says it does not have the context. Now we switch to user 2. Okay, this is user 3 with access to legal, general, and sensitive. So the authorization now succeeds, and it's going to come back with all the context that's able to retrieve. Okay, and the final part of this is that because we have a reference into the data itself, a user, if they have authorization, they can directly point to that specific document and use that as a context to do more targeted queries. Okay, I believe that's the end of that demo. All right. All right, that was the last slide, so we'll be happy to take questions. Yep. Yes.
Is the vector stored locally in the system, or is it external? Vector stored.
The question was if the vectors are stored externally or in the system. They're stored within the storage system itself. Yes.
So the question is that because there are different framework and also different implementation of the vector database, so do you allow customer to choose different ones, or it has to be used the one you're using the system?
The SDK currently supports LangChain and Llama Index. So as long as in the applications built using those frameworks, it will support those. Was that the question?
How about vector?
Oh, okay. Yeah, so that's abstracted away from the applications. So it's basically the database that we use internally, which and we do expose some of the features of that database. For example, the type of index, the type of similarity search, and so on. And that's available for the application developer to tune to their needs. Yep.
You were showing the RAG pipeline running on storage, right? So how do you scale the performance when the usage goes up?
Yeah, so one of the features of the architecture is what we call shared everything. So we have compute nodes that each have access to the storage over a shared NVMe fabric. So you can simply add more compute nodes to the cluster, and these compute nodes can have heterogeneity. So they may have GPU if they're required to do the special types of processing, while other compute nodes might have just CPUs for the regular storage processing. Right. So that's how we scale depending on the needs. The question was if we're using a vector database. Yes, currently it is using a vector database.
What are you addressing the challenges of re-indexing when you create the file or any embeddings delete? How you are updating?
Yeah, the question is how we update the vector database. Yeah, that's a good question. So a lot of vector indexes currently have limited streaming capabilities, and this is due to some fundamental algorithms used in the indexing itself. Right, the graph algorithm loses accuracy over time as you delete edges. So this is currently using the state of the art, but we do expect newer vector indexes to get more efficient at handling deletions, right? Anything you want to add, Anne?
Yeah, and we also store a reference to the data, so that with that we'll be able to figure out if it's deleted and accordingly do actions.
All right. Thank you.